Welcome everybody to the second lecture. If you can, if there are some questions from the last lecture, maybe we can have answers now. Let me just quickly put this. I don't see the chat, so if there's any question, maybe you can tell.
Don't bother. I'm here to help you
Okay.
with that.
Okay. So if not, yesterday we just like a quick review. Yesterday we saw maybe two important ideas. First, we saw that in general dynamical laws, like for example Newton's law, and now we will see, for example, the case of electrodynamics, they require an inherent space and time structure or space-time structure. In the case of Newton, we saw that historically he started with the structure of absolute space, absolute time, and absolute motion. We saw the problematics of these definitions. We saw how to fix it in terms of inertial frames, and then we saw that there is an even better description in terms of geometrical terms. But at the same time, we realized that by writing Newtonian dynamic in terms of geometrical terms, we discovered that the theory can be written in terms of coordinate independent concepts. And then that raises the question whether the definition or the principle that GR is in some way independent of coordinates makes it special or not, because we can see that Newton's gravity also can be written in terms of coordinate independent language. And let's say on the side of that, we can even see that we can express the Newton's gravitational theory also as in a coordinate independent way as also a curved spacetime. Okay, so both these typical features that are associated to GR, both the coordinate independent formulation and the notion of a curved spacetime, doesn't seem to be a clear idea that is only expressible in terms of general relativity. Okay, so with these two things in mind, we are going to now work with special relativity in this small lecture, and I will comment a bit more about the meaning of covariance and the meaning of invariance in the case of both special relativity and Newton's theory, almost more rigorous Galilean spacetimes. And then I will just finish commenting on that, and then tomorrow we will go for the case of GR. Okay, so let us start as we did with Newton. I think it's important to highlight what is the historical debate in terms of foundational issues of special relativity, because it will also highlight two things: the importance of the relativity principle. I mean, this whole course is called philosophy of relativity, so we really want to point out the importance of relativity principles in the construction of space-time theories. And then the second thing will refer to the fact that well, that basically we can accommodate better the importance of different theories if we follow the debates of the moments, because otherwise, if we are presented in a modern formulation, which we will go for, which is basically the Minkowski formulation of special relativity, we can maybe oversee some of the original ideas that were important for this construction. Okay. Okay, so let us start with electrodynamics. I will just go very briefly around that, because we all know how this works. So basically, after some historical development on the experimental side with Coulomb, Ampere, and Faraday, and so on, and other people, we had a very unified description of electric and magnetic processes, which can be beautifully described in terms of the Maxwell's equations that relate both of these structures. Plus the Lorentz force, which will tell us how motion, how charged particles are moved through space-time due to these electric and magnetic fields. Now that these are the mathematical laws, but already at that time there was a lot of conflict on what it really meant in terms of physical entities, both these magnetic fields and these electric fields, right? Even though that today we think about fields in a more clearer, transparent way, both in terms of matter content and also geometric content. At that time, it was not clear at all what it meant, right? And for Maxwell, he was one of the few ones, together with Hertz and some other people, that really thought about the electric and magnetic fields being material fields, okay? They were in some way not material in terms of like ponderable matter that we would know, like the charged particles, but in some way they would be materials because they could storage energy, okay? And then he also realized that waves, the electromagnetic waves, which are consequence of the laws of electrodynamics, they propagate in some similar manner to how waves propagated in optics. Now, that here it's the point where the ether comes by, because usually people, sorry, there's somebody with a mic on. Could it stop it? The notion of the ether, people are connected with electromagnetism, but it actually is first it was developed in optics, in optic systems, and then Maxwell realized that there was a connection between the ether of optics and the possible ether that could be present in electric and magnetic systems. So here's what he says. It appears that certain phenomena in electricity and magnetism leads to the same conclusions as those of optics, namely that there is an ethereal medium pervading all bodies. Okay. So basically the whole idea of this is that we would have a material entity, let's call it, that it's the ether, and then it would manifest in the form of electric and magnetic fields. Okay, that would be a bit the physical description. Now the problem with that is that we don't have a dynamical law of the ether. Maxwell tried to articulate one, but he failed, and actually nobody really success with that, because now we know that the ether is not there in any meaningful way. So, but at that time, this was the discussion, okay? Now, a more successful discussion around that time had to do not with the composition of the ether, but actually how it moves, or better said, how do we move with respect to the ether, and how do we see the consequences of that in the context of the Maxwell's equations, in context with electromagnetic fields. So here's where really the relativity principle comes by. Now, it's not very difficult to see that the laws of Maxwell, they are written in a form that already forces us to choose one privileged frame, which we could call the rest frame, because it's associated to the rest frame of the ether. Okay, so how we see that? Well, it's very easy. One of the possible solutions of the Maxwell's equations, which are electromagnetic waves, propagate with a given velocity, right? And this velocity is the velocity of light. Now we say it's constant, and so the moment we change a frame, and we are still, let's thinking about Galilean spacetimes. If we are thinking of changing a frame, now the velocity addiction rule forces us to change the velocity of light, which then contradicts the initial consequence of Maxwell's law. This means basically that if we still are fix ourselves in a structure of Galilean space and Galilean time, then we are forced to uniquely define one frame, which would be the rest frame with respect to the other, where the laws of Maxwell are valid, okay? Now, just to bother you a bit more with what we commented yesterday with this geometrical structure, this is a bit of a parenthesis, but I think it's quite interesting. We can actually define, remember that we introduced the Galilean structure, the Galilean space-time structure, in a coordinate-independent way as a collection of a manifold, a covariant derivative, and two other structures which had to do with how we slice the time slices of simultaneity, and then how we measure distance in each time slide by these other two structures, okay? Now, we can adds more structure to the space-time. In principle, we are allowed to do that. And actually, if we allow to add another structure, which is a vector field, only one structure, a vector field, then actually we are able to define a rest frame, okay? Now, this is exactly, if you remember, what Newton's absolute space was all about. We had a preferred frame. If you remember the picture I showed you, it was the way of thinking about this is that we had one frame, which in the picture is F2, which would say us, this is the preferred frame. And with respect to this frame, I can say what is in rest with respect to me, okay? So I could define absolute rest in this sense. Now, the way of doing that in a geometric coordinate independent way is actually adding a vector field. Okay, so actually, first of all, this makes us more stronger. It makes more stronger the idea that there is nothing really magical or mystical about absolute space. It's just assuming more structure, more space-time structure with this extra vector field than we actually require. Okay, because we know that the laws of, at least the laws of Newton, forget about electrodynamics for now, the laws of Newton can be defined without this vector field, okay? They are perfectly valid without this vector field, but we can still add it, okay? It's just a matter of making more complex what it's actually not so complex, okay? I will very briefly go with this, but you can see in Friedman's book about foundations of space-time this idea of absolute rest in terms of this extra vector field and how to construct this in a more formal way. But what I want to say about this is that electrodynamics, okay, in this again,
Uma
we are not
formulação
talking
geométrica
about
para a
Minkowski space-time.
eletrodinâmica.
Sorry, I
I'm
cannot.
sorry about that. I already muted the person.
Okay. So we still think about terms in Galilean spacetimes with this extra structure, okay, that defines a rest frame. We can actually use this vector field to construct a metric out of it, okay? Without this, we cannot, but with the extra rest frame, we can make this metric. Now, this metric should maybe sound familiar to you. And actually, I express it there in terms of, because we are still in flat space times, we can have some coordinates where we can define flat space. Actually, it's just the matrix with diagonal 1, -1, -1, -1, which is what? It's just the Minkowski metric, which afterwards we will see the name Minkowski, how it appears. But here we will see actually that we can rephrase the electrodynamical laws in terms of coordinate independent ways in this form with this extra structure. So we can actually, we don't require, this is a bit of a spoiler, right? That's what will come next, but we don't really require Minkowski spacetime to define this. But the bad side of this formulation is that, of course, we have an absolute space, a rest frame, a preferred rest frame, which does not obey the principle of relativity. And that is what is key here, is that we can argue that we can impose the principle of relativity, which we will do next today, and then we will see that, of course, then this all breaks down and we need another space-time structure. Okay.
Já vai ficar
Now,
disponível para gravar depois?
sorry, there are some questions. Maybe you can leave it for the end of the lecture.
Yeah, they just asked about the
your mics.
recordings, so you can just continue.
Okay. Now, what is the problem? Okay, forget now about the formulation. We have the problem that Maxwell's equations in terms of Galilean space-time or space and time can only be defined if we have one frame, which is the preferred rest frame of the ether. Now, what is the problem? The problem is purely physics, okay? There's nothing foundational here. And it's that we don't know what happens if we move with respect to the ether. Now, we have different experiments, but all of these experiments, at least historically in the moment they were developed, said different things. So we could think that first, the stellar aberration, I will not go through this, but in Friedman's book and there is in Bergsman's book, these experiments are quite well explained. It would take me another 2 hours to explain them. But the whole idea is that stellar aberration, in terms of the laws we have, forces us to assume that bodies move through the ether. They don't drag the ether along with it. So they basically move as nothing was there, right? But then we have the Fresnel's drag coefficient, the Fresnel's experiments that say that depending of the matter that the light is going through, it's partially drags the ether. Okay, so we have we have to also explain this, and then plus the Michelson-Morley experiment. The only way we can understand it in terms of space, of Galilean space and time, is that basically the ether does not drag the ether. Sorry, this is wrong. Okay, there's not the Michelson-Morley experiment forces us to think that the ether does drag the ether. Okay, it's not there. It does drag the ether. That's the only way we can explain the Michelson-Morley experiment. So we have, in principle, contradictory claims in terms of the ideas that we have about both the ether and how we move about it in terms of Galilean motion. So this, of course, brings about possible changes of the underlying assumptions. Now, historically, one of the first, before Einstein's paper, 1995 paper, was Lorentz paper. Okay, and what he tried to do is to really construct at first a dynamical account for the ether. Okay, he was thinking that it is important because he thought that the ether was as material as ponderable matter, which in his case would be just point particles with some charge. Okay, of course, this is previous all the development of particle physics and quantum field theory. So at that moment, this was the schematic definition that Lorentz proposed. He even offered some equations. They are very much related with the Maxwell's equations of how the ether is defined by two fields in this case, this D and H field, vector fields, and also a Lorentz force, which would tell how charged particles move through the ether. And then in his paper, he explains how to show that you could get the Fresnel's drag coefficient. So he could explain that. He could explain also aberration, the stellar aberration, because he thought that ponderable matter would go through the ether without dragging it in any way. Okay, the ether is not moved by the ponderable matter. So he could explain these two things, and we will see now how he does explain the Michelson-Morley experiment. But now a very important thing is that he already presented what is called, obviously, the Lorentz transformations. The question he asked is, how does this law that he proposes change if we are not moving a rest, like moving, let's say, as the ether, like in rest with the ether, but actually moving through the ether. Okay, so yeah, I have here like two images. So these are the two ways. Okay, we can think of the Earth moving through the ether in the rest frame. This would be the description that the equations use. But then, of course, there is the question of what happens if we think of us as being in the rest and the ether moving through us. Okay, how do the laws change? And then, I mean, this is one of the historically most discussed scientific discoveries. Well, like proposals of discovery, because actually it had to do a lot with what we mean by physical interpretation and or just mathematical artifacts, right? So Lorentz argues the following: let us assume that the ether defines some coordinates. Okay, we are in the rest frame with respect to the ether. By for labels that define the coordinates, and a body is moving through it without velocity. Okay, and we define it such that we choose our reference frames, which we can do basically as we wish, so that the velocity of the body just moves through the x axis. Okay. Now, if we would be in a if we assume, okay, as Lorentz did, we assume that we are in a Galileo spacetime. The transformation is the usual, right? It's just the velocity affects the position of the x coordinate. So if we want to see the effects of electrodynamics in our new coordinates of the body moving through the ether, we would have to do this kind of transformation, the Galilean transformations. Okay. Now, what Lorentz did is he added new variables, which is this prime variables, defined with respect to the coordinates of the body moving through the ether, like this. And then he connected it with the variables of the frame of the ether, like this. Well, already we can see, if we did a course in special relativity, that these are the Lorentz transformations of special relativity. But I want to comment on why he did that. Okay, this is not just a trick that he was boring and doing it. But actually, he did the following. This is the first, what is called the correspondence theorem. This is the first one. He actually did a second one that was more general, but it's sufficient to understand what he was trying to do. So let us assume that the ether defines some coordinates. Again, now we call it r, the position, and some t. A body moving through it will have, again, the Lorentz transformed, the Galilean transformed position. And now he introduced what he calls literally local time. Okay, he defines a new time that doesn't have to do with the coordinate time, the Cartesian time of the body, but just a new time that he didn't give any physical meaning to at this point. It was just a local time, a new variable, if you want to think about it. Now, he says the following, okay, his theorem of correspondence. If there is a system of bodies at rest in the ether frame and a solution of the field equations such that the electric displacement, the electric force, and the magnetic force in that frame are certain functions of r and t, there is a solution for the same system of bodies moving in the ether frame with velocity v, such that the electric displacement, the electric force, and the magnetic force in the inertial frames in which the system is at rest are exactly the same functions of r prime and t prime, okay, at first order and v divided by c. So basically, he's stating here that at least in the first order of the velocity divided by the velocity of light, which is a very good approximation because we, at least at that moment, we didn't have velocities. We were not experiencing relativistic effects. We can see that actually this new time defines also the same solution as the one of the ether. Actually, one can extend this to all orders in v divided by c, which then would obviously coincide with the Lorentz transformations. The problem at that moment, he didn't probably do the whole calculations, which takes some time, but he offered already this correspondence theorem. Okay. He derived two consequences, which are quite interesting, and also Einstein was influenced by it. First of all, that we can measure the relative motion of the ether with respect to the Earth. Sorry, I put R there, and the Earth at first order in v divided by c. So basically, that was telling us that the principle of relativity holds there, at least experimentally. We could not verify otherwise, it also served him to give an explanation for the Michelson-Morley experiment. Okay, the Michelson-Morley experiment is a second order experiment, which means that it's more in velocity divided by c. I will not
Antonio,
go too much.
there's a
I will
question
just
in the chat,
okay,
asking you to just repeat that part again.
Which part? The correspondence theorem?
I guess so. The person didn't. Yes, the person said yes.
Yeah. So basically what the correspondence theorem that he stated, okay, you don't have to see it in terms of Lorentz transformations, just what he's trying to explain here is that if you have the ether, okay, in some coordinates, r, which would be the vector r of position, three spaced vector, and some time, then you can realize that a solution of the whatever your Maxwell's equations give you as a solution with respect to this rest frame of the ether, you can find the same solution in another frame, okay, that is moving through the ether with this r prime, if you change the time, not to the Cartesian time, but to this notion of local time, okay, to this t prime. But this is only correct at order v velocity divided by c. Okay, this is important. That's why you don't see t prime or R prime must be in the Lorentz transformations, because this is just the first order. Then you can extend it to all the orders in this, and you get the Lorentz transformations. I think he did that posterior, but in any case, this is the correct answer. It's just that, of course, showing that the equations of Maxwell do that is quite a hard calculation. So he was just proposing this first paper. Is that the question that I have?
Yeah, he said he got it.
Okay, great. So basically going back to the Michelson-Morley experiment, he offered an explanation. Basically, what he realized is that, well, if I go back to the Lorentz transformations in terms of x prime, there is some contraction, right? It's called the Lorentz contraction that we now call it. And then he was trying to apply this to basically to the interferometer as a whole. So basically, he was saying, well, we are not seeing this effect that we want to see because of the Galilean transformations, just because we are not taking into account that the electric forces of that underlies the molecular structure of the material also underlies has some length contraction that would exactly cancel this effect and then give the Michelson-Morley null experiments. Okay, he gave an account about that, and I will not go through this because now we know it's well, we have a, let's say, better explanation. But I think from the philosophical science point of view, it's very interesting because it gives an important account on how do we value different explanations, that both of them could be true, but one of them has, let's say, more qualifications to be a better explanation, which in our case would be Einstein's explanation, with respect to another explanation, okay, that is, well, we call more ad hoc, but in many cases of historical science, it has proven to be also correct. So this is the typical example, but it's important to stress out that Lorentz at the time already gave very great ideas about how motion should be within electrodynamic systems, and obviously this influenced Einstein. Okay, so now we will go to the famous Einstein paper of 1905, the electrodynamic of motion of bodies, if I remember in English. So a big debate that had obviously spread out is whether Einstein knew about the Michelson-Morley experiment or not. He claims that he didn't. And then one question is, okay, if he did not know about the Michelson experiment, where did he get the whole idea of trying to postulate the principle of relativity as the key feature of his theory, okay? Did he just appear in his mind? The answer is no, and actually, I would recommend people to actually read the paper, which we will do. I will read literally what he wrote because he actually, I think he's very transparent in the way he writes and very pedagogical. So, as I say, for Einstein, the problem of electrodynamics had more to do with the fundamental assumptions, in this case of space and time, than sorry, I don't know, with the exit property. Than with extra hypotheses that take for granted these assumed structures. So instead of looking for how to add more physical explanations, he was actually trying to think what are the foundational issues. And he was probably motivated by the fact that, as you all well know, Einstein also proposed the photoelectric effect in similar years. He already knew Planck's discovery of quantum, the start of quantum physics. So, I mean, obviously he knew that something was missing in the foundational issues already of electrodynamics. Now, this doesn't mean that electrodynamics is wrong, and actually he took for granted electrodynamics, but in some way it was pointed out to him that we should maybe go back to the essence of the ingredients of our theories before just assuming that everything that we have worked so far is completely true, okay? He was very puzzled by the apparent asymmetries of rest and uniform motion in electrodynamics, okay? And let me just show you what he meant by this. So this is literally what he says. It is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. The observable phenomenon here depends only on the relative motion of the conductor and the magnet, okay? Whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. For if the magnet is in motion and the conductor is at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy, producing a current at the places where parts of the conductor are situated. But if the magnet is stationary and the conductor is in motion, no electric field arises in the neighborhood of the magnet. In the conductor, however, we find an electromotive force to which in itself there is no correspondent energy, but which gives rise, assuming equality of relative motion, the two cases discussed, to electric currents of the same path and intensity as those produced by the electric forces in the former case. So here Einstein was claiming that in some way electrodynamics was referring to two distinct phenomena, at least in the language, but in principle they are both the same, because we shouldn't take any preferred notion of one or rest or the other or the rest. In this sense, and actually that was the physical result, that the current was relative, okay? It doesn't matter if one is at rest or not. I think that the chat is multiplying the number of, I don't know if there are some questions. Okay, I assume no. So, as I say, he was puzzled by the asymmetry, and that's what he proposed to assume really the principle of relativity and maintain it as Newton did for any physical law. Okay. Also, he put away the ether. He didn't introduce it, and thank God he did not, so that he could really develop this whole theory without relying on the possible dynamics of it and so on. Since for him, one of the possible motivations about that is that we don't require, because we are really forcing ourselves to believe in the principle of relativity, we don't require absolute rest. So the whole notion of we need the ether to fix an absolute rest and so on didn't make sense anymore. We continue with Einstein's paper. Example of this sort, together with the unsuccessful attempts to discover any motion of the Earth relatively to the light medium. This is what I meant by the first order experiments, not the Michelson-Morley experiment at this point, but the ones that were done before that we cannot measure this relative motion, suggest that the phenomena of electrodynamics as well as mechanics possesses no properties corresponding to the idea of absolute rest. They suggest rather that, as has already been shown to the first order of small quantities, here he's referring to first order of velocity divided by c, the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. We will raise this conjecture, the purport of which we'll hereafter call the principle of relativity, to the status of a postulate, and also introduce another postulate, which is only apparently irreconcilable with the former. Namely, the light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. These two postulates suffices to attain attainment of a simple and consistent theory of the electrodynamics of moving bodies based on Maxwell's theory of stationary bodies. The introduction of a luminiferous ether will prove to be superfluous, inasmuch as the view here to be developed will not require an absolute stationary space, the rest phrase, provided with special properties, nor assigning a velocity vector to a point of the empty space in which electromagnetic processes take place. Okay, so basically he's saying all these kind of things. Now, if you want to think about what he gets so much about the velocity of light, well, actually, he tried to develop a ballistic theory of light, where the velocity of the source of light would be present before this, actually, but he didn't succeed that. So he just really thought about light being independent of the source emitted and just traveling with the constant velocity of light. Okay, so now the question is, how do we reconcile this, both, as he said, apparent contradicting ideas, right? The principle of relativity on one hand and the light with other. And the way he saw it was, okay, let us think about how we really are applying the relativity principle to begin with, which involves the notion of space and the notion of time. Let's go back to these definitions and see if they really make sense, okay? In the light of what we know now about physics. So in particular, he reconsidered the notion of time, okay? What time meant, and especially how time can be synchronized, or more generally, how can we know with our notion of time if two events are or not simultaneous, okay? I continue with his text. The theory to be developed is based, like all electrodynamics, on the kinematics of a rigid body, since the assertions of any such theory have to do with the relations between rigid bodies, clocks, and electromagnetic processes. Insufficient considerations of these circumstances lies at the root of the difficulties which the electrodynamics of moving bodies are present in context. So really, he meant that something is wrong, okay, with the roots of basic constructing clocks and so on and so forth, which basically means about the notion of time. Now, go back a bit on the notion of time. Remember that we had a notion of absolute time that was both true in Newtonian physics, and then as Newton formulated it, but also when we introduced inertial frames, which was basically saying, okay, we have an absolute true and mathematical time, which flows independent on anything external. But what is really meant by this, even though Newton didn't say explicitly, because he thought it was true, and basically all physicists thought it was true until Einstein, was that not only did it flow equably, you could show that it does, but actually that any point in space can measure the same time, and also inertial frames measure the same time. So what does it mean? It's basically geometrical, is that you can construct simultaneity slices, and they do not depend on the inertial frame. So both F2 and F1, they really see the same slices, S1, S2, S3, and so on. It's not that they are in one of them sees one time of simultaneity slice and one sees not. No, that's not the case in absolute time, okay? Now, if you see this physically, in Newton's time, this could make sense. Why? Well, because at that moment, we have first gravity, that gravity is infinite infinite velocity interaction, so it's completely simultaneous, so you could use it in some way, although it's very, you can have to imagine it because it's physically not possible. But you had also light, and light at that moment, even though it had constant velocity, finite velocity, one could always think about accelerating light and getting light more arbitrarily to be higher and higher and higher, so that in principle you could message somebody to synchronize your clocks in a more and more approximative way, so it's better and better and better, and then in principle this you could all agree at some point that time is synchronized, okay? And now the problem now is that since we have assumed that velocity is finite, this way of synchronizing clocks cannot be true anymore, okay? And we have to find out a new way of defining a synchronization of time, and how to see that two clocks, for example, that are far apart, how do they manage to say we are measuring the same time, okay? So the first part of Einstein's paper dedicated time to do that, okay? And the first part, he discusses a bit of what it meant by time by measuring the clock and so on. But here's where he really tried to define a precise way of measuring, of defining simultaneity of time. And as I say, I will read it because he just explained it perfectly, and there's nothing else to say. So he says, if at a point I have the picture there, okay? If at a point A of space there is a clock, and an observer at A can determine the time values of events in the immediate proximity of A, so whatever clock he has, by finding the positions of the hands which are simultaneous with these events, okay? So basically, he on his own, in some way with his clock, he says, okay, these events are happening. So if there is, and then if there is at a point B of space another clock in all respects resembling the one at A, it is possible for an observer at B to determine the time values of events in the immediate neighborhood of B, okay? But it is not possible without further assumption to compare in respect of time an event at A with an event at B. We have so far defined only an A time and a B time. Here's where he really is trying to avoid all prejudice about time that previous physicists had we have not defined a common time for A and B. For the latter cannot be defined at all unless we establish by definition that the time required by light travel from A to B equals the time. Sorry, I think this is more. Yeah, there it is. Equals the time it requires to travel from B to A. I think there is some part of the text missing, sorry. Yeah, forgot to. It's more than. Yeah. Let the ride of light start at the A time TA from A towards B, and let at the time B time TB be reflected at B in direction of A, and arrive again at A at the A time T prime. Okay. In accordance with the definition, we say that the two clocks synchronize only if this equality holds. So you have the picture, okay? So basically you start in A, sending a light, that arrives, this is he measures, when A measures TA when this light is emitted, B received this light, and the moment he received the light, he emits another light, and he measures the time where this happens, TB, and then TA, and then A measures the new light arriving at TA prime. And we say that both clocks measure the same, they are synchronized, they measure the same time only if this relation holds. So this sounds trivial, but Einstein is really taking its time to precisely define how to synchronize the notion of time and how to give a precise notion of time. And the consequence of that, as we will see, is that it forces us to think that time is actually, the synchronizing of time is actually a relative notion. It's not absolute, okay? He does that in the following of his paper. I will not go for that because you already know how this goes. Okay, you move you start with the same system A and B, and then you take another system that is moving with respect to A and B, and then you can actually realize that if it's moving, it will see this difference that I showed there with the denominator being different. So the synchronization is then not true. So two different reference frames, one at rest with the system and one moving at a system, they don't agree that these clocks are synchronized, okay? So the whole idea here is that synchronization is a relative notion, okay? It depends on the inertial system that we are moving with. The typical example that is put here is that, not this one, this, yeah. So here in the first picture, you see Einstein in the middle, and then there are two signals emitted from A to B, and somebody is moving, okay? And in this system where he's at rest, the middle Einstein, of course, he's saying, okay, yeah, these two clocks are synchronized. They are emitted at the same time. They emitted the light signal, okay? Now, if we now go to the position of the one that is moving, he will see, of course, that the light will reach the middle Einstein at the same time, but because of the constant of velocity of light, this means that actually he will see that A emitted the light before B. So actually, in his rest frame, he will think that the two clocks are not synchronized, okay? Because again of the constant velocity of light. Now then, the second part of the paper is basically dedicated with quite a lot of mathematics and some long calculations on how to deduce what we now call the Lorentz transformations, okay? How do two inertial systems see each other in terms of both position and time? And the big important thing here is that then we see that the absolute time notion that we had, this time function that I defined yesterday, is not absolute anymore, and two inertial systems that is moving with respect to each other in what we would call uniform motion, they would see different times, okay? If you are more a geometric kind of person, you can see also this kind of relativization of the time by just looking at the two pictures. So the left picture is if we assume that time is absolute, so we would have one time simultaneity light S, and then we have the light construction. we have the light cone structure, and if we maintain this simultaneity absolute time, we will force ourselves to think that the velocity of light will change with respect to the inertial frame 2, okay? Which is not what physics says. Physics says that velocity of light is constant with respect to whatever inertial frame. So the way of solving that is actually to rotate the time slice, as we see in the right picture, for the inertial frame 2, such that it maintains the cone structure, the light cone structure of our system as forced by the electrodynamics. Okay. Okay, so after Einstein proposed this in 1995, Minkowski took this work, okay, and he developed let's say the language we use today mostly, introducing a metric structure in Einstein's work. Now, Minkowski basically had in mind some work done, especially by Klein, that was trying to relate symmetries of some system, for a space-time system, for example, with geometrical structures. So he was trying to classify geometries by the underlying symmetries. And he realized that Einstein's result was something related, because we had some symmetries, the Lorentz transformations, and we can construct a geometry out of it. And the geometry in this case is we would have some manifold structure, in this case the four-dimensional real planes, and we would have what he called a Minkowski, what we call it now Minkowski interval, which is just a generalized distance function. It's not the usual Euclidean distance function, but a generalized distance function, such that these properties happen, okay? And then he defined it in terms of, as you know, putting the different sign with respect to the spatial components to the time component, okay? What we'll know now as a Lorentz signature, if you want to think about it. Now, this is valid only for particular coordinates, which are obviously what we call the inertial coordinates. So this resembles a lot the Galilean structure, where we had defined some laws that refer only to some particular coordinates that were inertial. And from there, we can realize that what this distance function, it's left invariant under the Lorentz transformations, okay? And this is how we can connect geometrical structure with invariance under transformations. Now, one can ask, as we did with Newton, if there is any way on generalizing it to coordinate independent formulations. And here the answer is even more commonly straightforward, as people know, because we only need to basically take what we know about GR, right? So here in this case, we can define the Minkowski spacetime as just two structures: the manifold, the differential manifold with all the properties we defined yesterday, plus a given metric with a Lorentzian signature, exactly as GR, obviously, that is flat in this case, okay? So we could say that it's just the flat version of general relativity, if you want to think about it. In this description, we can obtain exactly analog to Newtonian case, the Minkowski description in terms of distance function, and also all the kinds of Lorentz transformations, so on, that Einstein used. So comparing it to the Galilean spacetime now, you see that in the manifold structure is maintained, and then you see usually that here the rule is you have some manifold structure and then you add some geometrical parts. So in the case of Minkowski, we add a metric. In the case of Galilean spacetimes, we had to add an affine structure. Remember that with Minkowski spacetime, we don't need to add an affine structure, an affine connection, because the metric will give us already an affine connection, which will be the flat affine connection in case of Minkowski spacetime. But we had to add also the time, the time slice, extra geometrical terms, and a distance function. if we would be even more strict, we would add this other vector field that I showed, and then we would get what we call absolute Newton spacetime. So you see a bit how this works, right? Like we add some geometrical structure out to our spacetime, and we get different, if you want to think of it, different structures that define different laws in some way, okay? Now, we don't have, if we compare special relativity with Galilean spacetimes, we don't have absolute time simultaneity anymore, okay? That's the big idea that happened with special relativity with respect to Galilean spacetime. So we get rid of this time slicing. But both spacetimes are flat, okay? They share that. And also both spacetimes are coordinate independent, okay? So how can we then classify the differences between them, okay? So I think maybe, okay, let me just finish this and then we can ask if there are questions. So I want now to define two notions that usually in the literature you can find as being used one with the other meaning and so on. So they're confused, which is the notion of covariance and invariance. Okay, covariance is usually used in when we say that GR has the coordinate transformation as the covariant group. But also sometimes people say about invariant transformations. So here I want to be precise on what is the distinction between both of these concepts, at least in my description, which I use from Friedman's book, because it will be important for tomorrow. So let us assume a coordinate transformation, typical coordinate transformation that you know how to do. We said, so there's always exists a transformation, H. There is an automorphism, 1-to-1. It's a map between the proper manifold and itself that has some differentiability conditions, some continuity conditions, so on. This description more rigorously you can find in Friedman's book, such that this condition holds, okay? So we transform the point of a manifold with this automorphism, and then this condition with the coordinates hold, okay? So for any kind of coordinate transformation, we have this given transformation H and opposite. So you give me H, and I give you the coordinate transformation you meant by this transformation. So this is the first ingredient. And then we can use this H. The good thing about this H is that it's coordinate independent. So we can use it to transform any object over theory. So remember, we were playing with these objects, G, affine structure, DT, H. So these are our objects. We could have other objects like matter fields and so on. So for example, in gravitational theory, we would have the Poisson, the gravitational potential, the so on and so forth. So we can have all these kind of objects which are coordinate independent written. So this transformation, of course, transforms the object into another object that is defined like this, that I put there in terms of coordinates, because all kind of transformation H corresponds to a coordinate transformation. This is the requirement in terms of coordinates. And here becomes the distinction. So we say that a given space-time structure, whatever it meant, Galilean, special relativity, and tomorrow general relativity, is covariant under the transformation H if this new theory that we transform all the geometrical components with this transformation H is also the same space-time structure, okay? In our formulation, H is, of course, all admissible coordinate transformations. Why is that? Well, because we have defined our theories in terms of coordinate independent way. So, of course, the same laws, the same structure will hold with any kind of coordinates. So this covariant is just saying, yeah, all your coordinate transformations are admissible. All your theories are covariant under these transformations, including Newton's gravity in the way we formulated it, special relativity, and general relativity. Now, the extra definition is that we say that a given spacetime structure, again, is invariant under the transformation H only if this condition holds. So if each concept, if each part of the geometrical structure converts on its own. So it's invariant under this transformation, okay? So with these two ideas in mind, now, again, covariant is basically accepted for all theories. Invariancy is, of course, not true that all coordinate transformations leave the structure of geometry invariant. That is not true, okay? So okay, so I will just finish here by using the two space-time structures that we used. So since both Minkowski and Galilean spacetimes are flat, there are some coordinates that have some special place in these theories, which are the ones that makes the structure constant. So if you remember, I defined it yesterday, flat, for example, flat metric or flat affine structure and so on, as the one that we can always find coordinates that make the metric, for example, diagonal, or in the case of the affine structure, make the Christoffel symbols vanish. So, and then I call them the inertial frames, okay? So assuming this inertial frames, the special inertial frames or inertial coordinates, if we define it properly, then we can try to look for transformations H that leave invariant the geometrical structures. And then beautifully, and this is a bit, of course, you need to work a bit mathematics out of it. This is also in Friedman's book. You can find that if you do that with Galilean spacetime, so you try to find the transformations H that leave invariant. Obviously, the manifold will be invariant. That is trivial. But then the three other structures invariant, the affine structure, the time-like structure, and the distance H structure, then you realize that the transformations you get are exactly the ones you would expect, which are translations, rotations, and the Galilean. If we are a bit to Galilean transformations, transformations of this system, because obviously the rest frame is not invariant on the Galileo transformations. If we do the same with Minkowski spacetime, same procedure, we then can find that the Lie group in this case is also translations and rotations, which are trivial, but plus the Lorentz transformations now. Not the Galilean transformations, but the Lorentz transformations are the ones that leave invariant the metric in terms of inertial coordinates. So here we have the notion of invariance under the theory. And I will just finish here because of time, but I want to stress out that the importance of these both notions of covariant and invariance, because they will really get us to the point to claim something about general relativity and what makes general relativity special with respect to these both theories, for example, which in some way underlies the whole Einstein project that he had in mind when he developed GR. So I just wrote a small line to finish. All spacetime theories are covariant under arbitrary coordinate transformations. This is what we already saw yesterday and today. But there is a notion of invariant intimately related to inertial frames, and of course with the relativity principle. And we will focus more on this tomorrow. So I finish here, and if there are some questions, I'm happy to answer.
Oh, that's great. Thanks, Antonio. If anyone has any questions, you can just open your mic or say it in the chat. Okay, people are just saying thanks for your lecture. For now, at
I'm sorry
least.
if I'm doing too much physics in these two lectures, then maybe you're expecting more philosophy, but it is important that we define concisely these things so that maybe tomorrow we can discuss more about what it philosophically means for a theory. But of course, we need some background to do this. And I have omitted a lot of things, so don't expect this to be too rigorous. I would recommend you to take the books that I recommended if you will really want the whole deduction and the concrete proper explanations of this as I say in the books.
Okay, there's a question. The difference between Galilean spacetime and Minkowski spacetime is that Minkowski spacetime admits the relativity, right?
So as I say, the notion of relativity is not unique. So Galilean spacetime is relative, incorporates the principle of relativity in the way that it's invariant on the Galilean transformations. And then what you can do, and tomorrow we will try to see a bit about it, is that you can give a notion, a physical notion to the principle of relativity by saying all inertial frames see my theory the same. But of course, it has to do with how you define your inertial frames, right? And this is where special relativity and Galilean spacetimes don't agree with each other. They say different ways of defining these systems with respect to each other. So both can agree that they have a principle of relativity, but of course, how you define this principle of relativity, which has to do with the invariance under the geometric structure, differs between each other. Okay. So if you want to think about it, the one that does not have a principle of relativity actually is Newton's absolute space, because the structure of absolute space has only a one preferred frame. And if I transform it in any way with uniformity motion, then the structure changes. So it's not invariant under a transformation that has to do with a uniform motion and therefore with a relativity principle. I don't know if that answers the question.
Okay, it doesn't seem to have any more questions. Yeah, the slides will be available in the website.
Okay.
So
Perfect.
once more, thanks, Antonio. And I guess we all see you tomorrow in the usual hour at this time.
Yeah. Okay, perfect. See you tomorrow.
Thanks.